Hi guys, and thanks for attending my presentation on mesh validation. So my name's Dane, and I'm a senior applications engineer here at Hawk Ridge Systems. So I have a mechanical engineering degree from the University of Alberta, and I work in our furthest north office in Edmonton, Alberta. So that's why I'm wearing my long sleeve. It was almost 0 this morning when I left, so it was chilly. 0 Celsius, so like freezing, wherever that is in Fahrenheit. Today, I'm not alone, however. I got my colleague Silvio, and he's the product manager for simulation here at Hawk Ridge, and he's going to be monitoring the chat section. So while I'm presenting, if you guys have a question, type it in the Q&A portion of the chat. So on that column, I don't know what's right for you guys, but like on the column on the right-hand side, there's the Q&A by the chat pane. Type it into there, and it kind of categorizes it really nicely for us. So if you have any questions, don't hesitate to type them into that chat area there in the Q&A section. So if they're simulation specific, like, hey, can the software do this? Silvio will just answer that right on the spot. But if it's something specific to the model I'm showing or the problem I'm solving, then Silvio will put that to the side. And I got a little bit of time at the end for some Q&A. If not, I'll jump into one of those roundtable things and you guys can pick my brain there because I'll be hanging out around because if I'm here, then I don't have to do real work. So that's my goal. But if you have questions, put them in the chat. Silvio's awesome. He'll answer them for me, doing all the hard work. I get to have fun up here. But let's jump right into this presentation. So the agenda for the hour, and I'm going to turn off my camera because it's going to block my screen there a bit. So goodbye. But the agenda for the hour goes as follows. I'm going to introduce what a mesh is and why you need to validate it. Then I'm going to go over some simulation basics while introducing the practical problem that I'm going to be using as an example. Once I have a solution for that example, I'm going to introduce numerous automatic and manual meshing techniques for proving mesh convergence. I'm going to explain the pros and cons of each method so you can be confident when using them in your simulations. Finally, I'll mention some presentations happening later in the conference, as well as some of the more advanced simulation offerings from SolidWorks and Dassault Systems. So for that manual mesh section, I've shared an Excel template. So if you scroll up to the top of the chat there's an Excel file that I shared, and you can download that. You don't need to download it now. It's not like you're going to be able to follow along. I am using some movie magic to cut down my simulation time, just to condense it all into an hour here. But if you're like, hey, that was really cool, you can download that. Feel free to use it. I use it all the time. I feel like it saves me a bunch of time, but to each their own. So I'll talk about it later. If you like it, it's there for you if you want it. But let's get started. So what is a mesh? So CAD geometry can often be complex. So the finite element method uses a discretized mesh to break the problem into smaller, manageable geometry. A mesh is used to divide the geometry up into smaller volumes of known shape, and those volumes are called elements. So this collection of elements is what make up the CAD geometry, and that collection of elements is referred to as the mesh. So the elements have a simpler geometry, making the governing physical equations easier to solve. So most meshes are made up of thousands of elements. Let's visualize the FEA process with a simple 2D example. I want to measure the length of this curved path, but all I have is a yardstick. So in order to estimate the length of the curved path, I have to break it into straight segments. I need to measure those straight segments with the yardstick and then add them together to get the final length of the curved path. So you can see the actual solution is the red curved path, and my approximated solution, using my nice little yardstick there, are all those little discrete black lines. So in this example, those linear segments of the line can be considered our mesh, with each line segment being a single element. The more elements we have, the more terms in the equation we would have, causing a longer calculation time. So the mesh directly influences the solve time of our solutions. The more elements a problem has, the more equations are needed to solve it, therefore increasing our solve time. The other half of the balancing act is the solution accuracy. So as we can see in the bottom right-hand corner here, the yardstick cuts the corner and does not follow the curvature of the path. The large linear segments are a rough approximation in some areas. Now, let's imagine if we used a desk ruler instead of a yardstick. We go from 4 measurements to 11 measurements. This will give us a better approximation of the length in this area, but it's definitely going to take a lot longer to do. Imagine measuring out that 4-yard section with a 30-inch ruler. It's going to take forever. So that parallels perfectly with simulation, because the denser your mesh, the more accurate the results, but at the expense of solve time. And this is really what this entire presentation is going to be about. So FEA does that exact process, but with 3-dimensional tetrahedral elements instead of 2-dimensional lines. Each one of the tetrahedrals is called an element, and the red points at the end of the element are called nodes. So that little graphic on the right-hand side, that's one single element. Those red nodules are nodes. So the displacement of each node is calculated from the applied loads, and that displacement is used to determine the internal stresses of the part. Now, the best thing about SolidWorks simulation is that all of those calculations are happening in the background, and you don't really need to worry about it to run some simple simulations. So there are 3 element types in SolidWorks simulation. We have our shells, beams, and solids. So shell elements are ideal for thin planar geometry with a uniform thickness like your sheet metal or surfaces. Beam elements are great for structural systems like those created by weldments features, as they greatly reduce the complexity of the problem and have some unique pre and post processing options. So due to time constraints, these element types will not be covered in this presentation, but if you're interested in learning more about them, I highly recommend the simulation training class offered by Hawkridge Systems. So I've posted that link in the chat for anyone who's live, so scroll up. That link's there if you're interested. But if you're watching this later, I will post that link in the description of the video so you can have access to that as well. And the best thing about the class is that I might be teaching it, and yeah, you get to listen to me some more. So the most common element type, and the default in most cases, is what's referred to as a solid element. So solid elements are defined as tetrahedrons or triangular pyramids. Draft quality solid elements have 4 corner nodes, linear edges, and planar faces. Each node has 3 degrees of translational freedom, but the edges and faces have to remain linear and planar. High quality solid elements have 10 nodes. They have 4 corner nodes and 6 mid-side nodes. The edges can have a second order polynomial solution, making them better for mapping curved geometry because they're not restricted to the planar faces and linear edges. They can get a second order polynomial curve in there. So the total degrees of freedom of an element is 3 times the number of nodes. 1 degree of freedom for each translational direction. So it can translate in the X, can translate in the Y, and it can translate in the Z. The more degrees of freedom a simulation has, the more equations are needed to solve it. Degrees of freedom are a measure of the mesh density and the mesh's influence on the simulation time. So you're going to hear me using degrees of freedom, and that's all that means is I'm basically going to use that to substitute solve time. So draft quality mesh is a really good way to reduce your simulation time when you're testing things like boundary conditions or your contacts, or if you're mainly concerned with the displacement and not the stress values. So again, like in the general presentation, when the presenter said that, yeah, start simple with your simulations. Draft quality is about as simple as you can go. So it really cuts down on the time so you can test all of your contacts, boundary conditions, anything you need to test. So in the finite element method, the CAD models are broken into smaller volumes called elements. Solid elements take on a tetrahedral or triangular pyramid shape and come in 2 qualities. Draft quality elements have 4 nodes, linear edges between the nodes, and planar faces. This linear geometry makes them not ideal for curved geometry or volumes where you'd expect deformation because you'd need more elements to fit curves accurately. Each node has 3 translational degrees of freedom, giving each element a total of 12 degrees of freedom. Draft quality elements are great for a first pass to test boundary conditions or contacts, and for assemblies where you're not really interested in the stresses of those draft quality components. High quality elements, on the other hand, have 10 nodes, a second order polynomial edge, and curved faces. So in the 3D example I have on the right hand side there, some of the edges are linear and some of the faces are planar, and that was just for simplicity's sake. So they all have the option to deform to that curved shape, but I just chose to make my life easier and only curve one of them. So that ability to have curved geometry makes mapping to curves and deformed shapes easier with fewer elements needed. Each node has 3 translational degrees of freedom, giving each element a total of 30 degrees of freedom. High quality elements will take longer to solve because they have more degrees of freedom, but they do map better to curved geometry and will require fewer elements to get accurate results. So now that we kind of understand what a mesh is, let's look into why it's important to actually validate your mesh. So like we saw with our 2D path example, discretization can cause some errors when it's too coarse. This parallels nicely with the 3D finite element method. SolidWorks simulation will give you an answer, but it's up to you to prove that it's independent of your mesh, or that your answer doesn't change if you change your mesh. So there's a few ways to validate your mesh. The first would be just a visual inspection of the mesh. You can compare the nodal and elemental solutions. You can look at the energy strain error, or you can refine the mesh until convergence. So what that means is you just use smaller elements until the value stops changing, kind of like we did with the path example. So due to time constraints in this presentation, I will talk about visual inspection and refining the mesh until convergence, until stress convergence. If you're interested in the other 2 validation approaches, I encourage you to check out our simulation training class provided by Hawkridge Systems, because it'll go more in depth into those other ones because we have more than just an hour. So we can initially gauge the quality of the mesh with a visual inspection. The elements should be one uniform color, and the nodes of a single element should not have a drastic change. When looking at thin areas, it's a good rule of thumb to have at least 2 high quality elements across the thickness of a part in order to account for bending. So the image at the top here, this is an example of a poor quality mesh. So we can see that the top nodes of the element in the middle are red, and the bottom nodes are blue. Keep in mind that the color scaling is not constant throughout different studies and can sometimes be deceiving. So taking a qualitative measure is a really good backup. So looking at the node flags, we can see that the bottom elements have about 121 megapascal difference from one node to another. That's about a 60% difference. That's a sign of a low quality mesh and unacceptable in most engineering scenarios. So this image, however, is an example of a high quality mesh, and we can determine that with a visual inspection because the elements are all one color. Probing the values at the nodes, we can see a difference of 0.5 MPa of the nodes in one single element, or about 0.7% change. We can also see a smooth transition of green to blue distributed across many elements. So all visual signs of a good mesh. So looking at both the images together, we can start to develop some initial insight into determining mesh quality from a visual inspection. The high quality mesh has elements that are one color and a small change in value of its nodes. A more qualitative approach is to refine the mesh until convergence, until stress convergence. This can be an automated or manual process inside of SolidWorks simulation and should be done to every study you're using to make design decisions with. The procedure is to record the stress value at the area of interest, refine the mesh, and then record the value again. If there's a significant change, you repeat. If there's not a significant change, then your stress value has converged and you know that your mesh is independent from your solution. So in this image here, the first study, so the one in the top left of your screen, we have a stress value of 284 megapascals. The second study is just below it in the bottom left, where the stress value changed to 265 megapascals, so it went down a bit. That was a significant enough change for me to warrant another study. The next level of mesh refinement is in the top right, where the value changed to 269 megapascals. So that's a less significant change, but we're going to look at one more level of refinement just to be sure. The bottom right image has a very fine mesh, and we can see the stress value did not change significantly, so we can be confident that our stress value is correct, assuming our boundary conditions, material model, and study type are all valid. So keep in mind, these changes were brought on from the mesh. I didn't change any of my boundary conditions, just the mesh density. Displacement is the primary unknown of the FEA process. So the displacement results will converge with a coarser mesh and larger elements. The strain is calculated from the displacement and the stress is calculated from the strain. This chain causes the stress and strain to need more refined mesh to yield accurately converged values as compared to the displacement. So the displacement will always converge before the stress and strain values. So make sure that you are proving convergence for whatever you want your solution for. If you want to know your stress values, you don't really need to prove convergence of the displacement. You got to prove it for the stress. However, if you prove convergence for stress, your displacement will be converged because it converges first. So to summarize, it's important to ensure your solution is independent from your mesh. Without mesh validation, you don't know if you're looking at accurate results or just a rainbow spectrum over your model. So in the next section, we're going to review some FEA basics and then define the example we're going to prove convergence with. So the basic FEA process can be broken down into 4 parts. You have your CAD modeling, pre-processing, solving, and post-processing. The CAD stage is where you model the geometry that you want to analyze. Creating a separate FEA configuration or model is ideal, so you can modify the geometry without affecting the final manufactured component. So SolidWorks has references. If I change the model, it's going to update the drawing. When I'm making little tweaks in simulation, I don't want to mess with the drawing, so I always make my own configuration or my own unique model. Some modifications that you could do might include simplifying the geometry by removing unnecessary and small features that might be element hogs, creating split faces to apply boundary conditions to, and being able to manipulate model dimensions to run parametric design studies. So in the FEA pre-processing stage, you choose the analysis type. So the SolidWorks simulation portfolio has options like linear static, dynamic, nonlinear. You can also define your material model, which simulation has a robust library of. Next, you apply the boundary conditions like loads and fixtures, and the final step of the pre-processing stage is to create the mesh. After that, you run the solver, which is based off your study type and conditions like degrees of freedom or number of contacts. When the solver finishes, you can begin the post-processing results like displacement, stress, natural frequency, temperature, factor of safety, and really many more depending on your needs and the specific study type. So since this presentation is focused on the accuracy of your simulations, I'm going to talk about the sources of error and uncertainty in this mathematical model. So this bar graph here represents the relative significance of error from each portion of the mathematical model. So in the CAD model, the geometry is ideal. So when you say something's 10 millimeters in SolidWorks, it is 10 millimeters. In reality, there are manufacturing tolerances. So each part you manufacture could have a different size. There's wear. So parts can get used down, they can wear down like this nice uneven brake pad here. And there's even surface roughness and imperfections. So what SolidWorks thinks is perfectly flat and planar, you zoom in real life and it looks like not flat and planar. And then there's other imperfections as well. So these anomalies are usually insignificant, but they can account for some error when comparing your simulations to real-world empirical testing. The material model you use is the next source of potential error. SolidWorks has a robust material library giving you values for material properties like yield strength, Young's modulus, and Poisson's ratio at standard temperature and pressure. The default material models are for ideal materials at ideal conditions. So customizing is available for temperature dependencies, orthotropic materials, and some other unique situations. So due to material imperfections, pre-stress from manufacturing, and material model assumptions, there is a small amount of uncertainty and error in the material portion of the mathematical model. So loads, those are things like forces, pressures, or torques that are acting on your model. Whenever you're putting loads into a simulation, you're trying to predict and simplify real life scenarios. With known use cases, it's hard enough to create equivalent forces, but it's almost impossible to account for misuse and abuse of products. Someone will always try and use the product in a unique way, and predicting all the force magnitudes and directions is near impossible. This uncertainty of the unknown adds a significant amount of error, so overestimations of loading and factor of safety constraints are kind of used to compensate for misuse and abuse. So fixtures are necessary for simulations in order to hold your models in place and not have them accelerate once a load is applied. Fixtures tend to add extra stiffness to the model and can create large error or uncertainties in the model. Luckily, this error is very localized and does not affect global results of the simulation. So even though fixtures have the most significant amount of error, we also have the most control over this error as well. So in order to have accurate results, you need to make sure that your area of interest is significantly far away from a fixture. So today I'm going to be using a linear static study to solve my problem. With simulation, you can simulate assemblies or multi-body parts. In order to define how the components interact, you can add connectors. There's even specific connectors to help you validate bolts, pins, springs, and bearings. You have lots of control over fixtures as well. You can apply them to faces or edges, choose which degrees of freedom you want to restrict, and can even add a stiffness to a fixture. Additional loading types are available, like temperature, prescribed displacement, gravity, torque, and you can even replace the weight of bodies with an equivalent force. So there's 3 meshes available that have the ability to selectively and automatically refine your mesh. And there is a huge range of post-processing to solve almost any engineering problem, and can even use a product design insight plot to help optimize your products. And finally, you can do multivariable design studies where you can manipulate dimensions, material properties, and boundary conditions to really hone in and optimize your designs. So for our example, I want to validate the mesh for this compliant test mechanism that I want to 3D print. Before I print it, I want to have an understanding of if the compliant cylinders will stay within the elastic range of the material and how much force I need to apply in order to get the range of motion I desire. But before I can draw any conclusions from my studies, I have to validate my results and prove that my solution is independent of my mesh. So again, the latter portion is what the focus of this presentation is going to be on, validating my results. Not really going to draw any conclusions from it. So before we get started, let's make sure that our simulation meets the assumptions of a linear static study. So are my boundary conditions static? So I'm planning on holding the pawl in place and then seeing how that stresses out the part. So yeah, that's scenario static. I'll only be evaluating the moment the pall is in the predefined position. Is the material going to stay in the linear elastic range? Well, I hope so, or else I'm going to have to make some design changes. This one's kind of easier to determine after the study's run, so let's just assume yes for now. So, small deformations. Well, I don't really expect the compliant mechanism to deform too much, but SolidWorks will let me know if I breach this assumption. So again, we're just gonna assume yes, and let's start the study. So for this test print, I want to understand the stresses induced by operating the compliant mechanism. In order for the pall to release the gear, I need 4 degrees of rotation. Since I don't know how much force is required to cause 4 degrees of rotation, I'm going to use the prescribed displacement boundary condition. This will allow me to force the model to rotate 4 degrees and compute the force required to cause that displacement, as well as the internal stresses in the model. So the prescribed displacement tool is a fixture. I'm going to apply the fixture to the thumb button of the pall using the blue selection box in the property manager. In order to add a prescribed rotation, I need to define an axis as reference geometry. Once an axis is selected as a reference geometry, the coordinate system changes from Cartesian to cylindrical, allowing me to add a rotational component. I'm going to toggle on this circumferential direction, and I'm going to put in 0.07 rads, which is about 4 degrees. And then, of course, this process is repeated for each sized pall. The central cube faces are entirely fixed, meaning they cannot displace in any of the translational directions. This will concentrate all the stress in the connecting cylinders, which is what I want to test. Looking at the results, I can see the stress is the highest at the connection points, and that's kind of what I was expecting. Doing a visual inspection of the mesh, we can see a weird stress transition at the end of the thumb piece, which is a cause for concern for the mesh quality. The cylindrical portions do have a smooth color gradient, but that could definitely be improved with some refinement. So now that we've run the study, it's time to verify our solution using these convergence techniques. So SolidWorks has 2 tools to automatically refine the mesh: the hotspot diagnostics tool and the adaptive meshing simulation options. The stress hotspot diagnostics tool detects regions of the model where stress gradients between adjacent elements are irregular. In certain cases, these irregular high stress gradients can be attributed to stress singularities. Once stress hotspots are detected, they're displayed on the screen, and you have the option to select which areas you want to refine and which you'd like to ignore. After the mesh is refined, you have the option to display a convergence plot for the areas of interest, and you can export that plot to Excel. The tool will also detect stress singularities in the geometry and the mesh. So a stress singularity is a place where stresses are theoretically infinite. So let's think about the example of a point load. When you apply a load to a point which has no area, the stress is infinite because the force is divided by 0 area. Some other conditions that create singularities are boundary conditions applied at a point, geometry with a sharp inside corner, and sharp corner contacts. So stress singularities are a source of inaccuracy and are completely dependent on your mesh. They're a problem in any FEA software, but luckily, they only have a small local influence on our stress values. And we're going to look at some ways to work around them. So we are going to use the stress hotspot diagnosis tool, which is found by right-clicking on the results folder. And the first window in the property manager allows us to adjust the sensitivity. This slider can be adjusted to target or ignore singularities. After you click the Diagnose button, a pop-up window will appear indicating whether or not the model has stress hotspots. And we can see, ta-da, and it makes that cool sound, stress hotspots are detected. So the second window of the Property Manager allows you to isolate the stress hotspot regions and run a convergence test. In the graphical preview of the stress hotspots, we can see that the gray areas are regions where the mesh is not refined enough to give accurate results. The hotspot tool will isolate entities in the targeted regions and allow you to run a convergence test by reducing the element size in those areas. You can do a total of 3 runs or levels. So in this example, each mesh refinement level will reduce the element size in half. You can manually select specific entities to refine, but I'm just going to use them all. You can also choose to use the refined mesh or keep the original mesh with this radio button down here. But let's update the values to the new mesh. And then finally, clicking this Run Singularity button will automatically do a mesh convergence test for us on those selected entities. And I'm going to use my movie magic here. Ta-da! So the pop-up window tells us that we have a singularity in our model. The final window in the tool allows us to plot a convergence graph of all the entities of interest. Looking at this plot, we can see most of the lines begin to converge, except this line at the bottom, which doesn't really level off and it kind of doubles in value. So back in the Property Manager, I can isolate a plot for edge 3 and see the divergent nature of this stress singularity. So now that it's all by itself, we can really see that, okay, this value is changing drastically every time. So we can run another 3 refinements again to get new data points for our convergence plot and really prove convergence. With this hyper refined mesh, we can see that all of the edges clearly converge except that edge 3 where the singularity is. It just keeps jumping up in value and passing some of those other areas. So from this tool, I can determine that my boundary conditions are creating a stress singularity. So we can see right here where that fixture is. But it's kind of ignoring my cylindrical connections, and it's not being triggered by the hotspot diagnoses tool because the elements there have a smoother stress gradient with their neighbors. So it focused on that hotspot of the stress singularity. So the hotspot diagnostic tool was great for detecting stress hotspots, refining the mesh in the area of those hotspots, producing entity-specific convergence plots, and detecting singularities. It's a great tool. Let's look at another automated mesh refinement tool inside of SOLIDWORKS simulation called adaptive meshing. So the adaptive meshing tool will refine or coarsen the mesh based on user input accuracy values. After the mesh refinement, you can produce a convergence plot for the maximum stress. This can be finicky sometimes as the maximum stress location could change as your mesh is refined. You can export your convergence data to Excel, and it's not limited to 4 data points like that hotspot diagnosis tool. It'll give you data for however many passes that occur. So this tool does not allow user input on where to refine the mesh. So it can sometimes be more difficult to avoid singularities, and it can get really caught up on them. So the H-adaptive method is only available for solid elements. So adaptive meshing is turned on in the study properties. There's 2 types of adaptive meshing, but we're going to focus on the H-adaptive method because it refines the mesh by adjusting the number of elements like we've been doing this entire time. The target accuracy value will adjust elements that don't meet the criteria. This slider looks at the difference in the strain energy norm from 2 consecutive runs. The energy norm error is the difference between the nodal and elemental solution. So we're setting the accuracy slider at 99%, which means that the first run and second run have a 1% difference, then a third run will be done. The accuracy bias slider can focus on local high stress areas or the global overall mesh. If your model has a singularity, setting this slider to a global level can avoid focusing on the singularity. We're going to leave ours kind of in this mid-range to see how it handles the singularity. In order to not run indefinitely, we're going to set the number of iterations to 5 loops. This setting will give a maximum of 5 iterations before giving me access to the post-processing tools. The checkbox for mesh coarsening will help us conserve elements and solution time by coarsening the mesh in areas where the strain energy norm is beyond our desired accuracy. So hitting OK on the settings and clicking run, the study will start the iteration loops. We're going to end up seeing 5 iterations happen with a progressively smaller mesh. So looking at the mesh, we can see that the mid-range accuracy really focused on the area of the singularity. Right-clicking on the results folder, we can create a convergence graph for the maximum von Mises stress value. We can see that the graph is clearly divergent and we have a singularity. The mesh in our area of interest has been refined, but was definitely not the target for the refinement. Since this adaptive method does not store the values for every iteration, we can only display a convergence plot for the maximum stress value. We have no evidence to prove convergence in our area of interest. We can, however, create a global accuracy plot by using the convergence graph tool and selecting target accuracy. This tells us that overall, there's about a 4% error in our mesh. So depending on how far away you are from yielding, could be good, could not be good enough, but overall, globally, our mesh has about a 4% error. So let's try this method again with our accuracy slider set all the way to global. And let's see if we can ignore that singularity value. So looking at the results, we can see that the singularity was not ignored, but it was not the sole focus of the refinement. Looking at the mesh and the cylindrical connections, we can see that the mesh has been refined, and we have a really nice looking color and stress distribution across the feature. Some other areas of stress concentration were refined as well, like the transition of the thumb piece and the back of the pawl here. To make the best use of the tool, I'm going to create a new study with forces instead of fixtures to remove the singularity. In order to know how much force was used, I'm going to evaluate the reaction force of the fixture by right-clicking on the results file and clicking resultant force. Selecting the faces with the fixture, we can see the force required to hold the pawl in that position. These values are going to be compared to empirical data on finger strength to determine the best size of the compliant mechanism. In a new study, the prescribed displacement fixtures are replaced with the appropriate forces. Looking at the results, we can see drastically different deformation behavior. This is because the fixture forced the face to be rigid, but the force value allows the face to deform more realistically. The stress is now concentrating on the neck of the thumb piece more drastically, especially in the stiffer pawl that had that larger force on it. So let's run the adaptive mesher and see what happens. I'm going to leave the bias in the middle and do 5 loops. Looking at the results, we can see we have material failure on the larger connection. Checking out the convergence plot, we can see that the value starts to settle on 147 MPa. So the mesh in the connection region looks good, and it's below yield. So my connector's looking good, but now I have this really high stress on my thumb piece. So after all of that, which scenario is more accurate? The prescribed displacement or the applied forces? Well, the prescribed displacement and the force boundary conditions were yielding different deformation plots in the area that they were applied. This variation in deformation was causing the stress distribution to change, producing these drastically different results. Now, which one of these shapes is correct? So if you remember in the beginning, we were talking about sources of error and how fixtures can create added rigidity to a structure. This is a prime example of that. So the prescribed displacement tool keeps the face that the fixture was applied to as rigid. This is causing the linear shape that you can see on the image on the left. The image on the right has the applied force. You can see the face where the force is applied can deform, giving us a more realistic deformation plot and stress distribution. So in the area near the fixture is causing some error due to the extra stiffness that it generates. We can see that the added stiffness of the fixture is also affecting the stress in the cylindrical connection. The error of the fixture is reaching into our area of interest, so it's not far enough away from the fixture or that singularity that it generates. To wrap this all up, the applied force simulation will yield results more closely related to a scenario where a thumb would be pressing on the button. In reality, the face would be able to deform and create that bending moment, which is concentrating the stress in the area of the direction change. The prescribed displacement tool was really useful for determining the amount of force necessary to get the motion we wanted out of this compliant mechanism. We used that force for the applied force study, which was a lot easier than trial and error or a parametric study. So the automatic mesh convergent tools were great at finding singularities and proving convergence in our area of maximum stress, but we still have not proved our solution in that cylindrical connection. So now we're going to look at some manual mesh refinement techniques for that. In SOLIDWORKS simulation, you can manually adjust the mesh in areas of interest using a tool called Mesh Control. This Mesh Control tool allows you to select entities and define the mesh size you want on that entity. This allows you to ignore locations with singularities. You can target areas that are not the maximum stress values and use tools like split face and sensors to quickly get the data from the area that you want. The convergence process is the main con to this method, as you have to plot the data manually. However, the use of sensors and an Excel template can make this a less redundant task. So to begin the manual mesh refining process, I'm going to create simulation sensors in my area of interest. I like to do this in the Model tab so my feature tree is bigger. At the top of the feature tree, you right-click the sensor folder and add a new sensor. For the sensor type, we want simulation data, and for the quantity, we want the von Mises stress, as that's what we're using for our failure criteria. In the sensor properties, we want to change the criteria to look for the maximum value over selected entities, and then select the two faces making up the cylindrical connection. We're going to make 3 separate sensors so we can read the stress value of each connection independently. In the feature tree, we're going to rename this sensor so we know what it's doing. And of course, that same process was repeated for those 2 remaining connection points. So now that we're monitoring the stress values in the area of interest, let's run a study with a coarse mesh to use as a baseline for comparison. For this study, I've decided to apply a force of 150 newtons because that's below the average grip strength of a person and really about as hard as I want to squeeze this release mechanism. Once we have our results, we can expand the sensors folder and see the maximum stress values in my 3 compliant connections. In order to verify these numbers and actually prove convergence, we're going to run more studies with successively finer mesh. We're going to start by copying this study, so then I don't have to redefine my boundary conditions. So this is done by right-clicking the study and selecting Copy Study. We're going to give this new study the name MC for Mesh Control, because I'm going to be applying a mesh control to it. In that MC study, we're going to apply a mesh control on those same faces that we put the sensors on. To access the mesh control tool, right-click the mesh folder and select Apply Mesh Control. In the Property Manager, we can select all the faces of interest in one operation. And we're going to set the mesh size to 0.2 inches. Next, we're going to copy this study and edit the mesh control feature. Copying the MC study saves us time as we're not going to have to redefine the boundary conditions in the mesh control. For the MC2 study, we set the element size to 0.1 inches. I'll repeat this step 3 more times to ensure I have some nice data points for my Excel template. I continued the pattern of reducing the element size and the area of interest in half. So now that I've defined all my studies, I can kind of run them all in sequence, freeing me up to do something else while these studies solve. So hitting the arrow under Run This Study, we can choose the option to run multiple studies. I'm going to do that and choose all those MC studies to run. So while these are solving, let's take a look at that Excel template that I created. So the template I've created and shared with you guys in the chat up there will create a convergence plot and tell you the % difference of your degrees of freedom and stress values. All you have to do is fill in the blue sections. To start, I'm going to rename my areas of interest to their corresponding names. This is going to automatically populate in my chart's legend and make the data easier to read. Splitting my screen into 2, we can do some quick data entry to grab the stress values and degrees of freedom from each study. So starting off with the course mesh baseline and using the sensors and the feature tree, I can easily read the stress values at my area of interest and put them into my Excel chart. To get the degrees of freedom, I need to right-click on the results file and select Solver Messages. Now, onto the study with a mesh control. As I input a value for the stresses and degrees of freedom, the plot starts to generate, and the % difference between the 2 studies is calculated. So let's kind of fast forward to a more completed table here. We can see that the values were basically accurate with the original mesh, but now we have proof. Looking at the % difference table, we can see the difference between M4 and M5 studies in relation to degrees of freedom changed by about 80%, but the stress values changed by around 0.1%. This is a sign that your solution is independent of your mesh and convergent. Looking at the plot, we can see the lines are horizontal, again, pointing to the fact that the stress values are convergent and that our solution in the area of interest is independent of our mesh. So that concluded the section on mesh and mesh convergence. I'm just going to briefly talk about some of the offerings here at Simulation and then open it up to questions. So we have some later presentations focused on simulation. Damon's doing one on flow, Ryan's doing one on assembly analysis for FEA, and then Terrence is doing a Simulia offering as well. So this is kind of the product line for SolidWorks simulation. It is broken into those 3 familiar tiers, all with a whole bunch of different study types. Then there's the CFD, a flow simulation. There's a plastics for the injection molding process, and then Simulia Abacus for your more multi-physics and complex simulations. So you can see that there's a lot of overlap of these products. So if you have a specific simulation need, I strongly encourage you to reach out to a Hawkridge representative and we can kind of hone in and find the best software for your specific issue. So this right here is an example of kinematic motion simulation inside of SolidWorks Simulation Standard. You can find forces generated from motion, gear ratios, forces resulting from motions, and much, much more. There's topology optimization, which you can use to maintain the stiffness, but remove some of the mass and get some really cool organic looking shapes. So this would be awesome for some of the 3D printing technology that we offer as well. This is an example of a drop test. So it's a little bit of a dynamic event that you can do in SolidWorks Professional. And then there's the SolidWorks Nonlinear, where you can start answering questions like, what happens post-yield? Can I model rubber? What if my structure deforms? How do I represent complicated part interactions? So these are some examples of those nonlinear studies. So the spring at the top has some large deformation. Large deformation. Hyperelastic materials like the rubber being compressed in the top right. And then your nonlinear contacts like you see with those two images at the bottom. Then there's Simulia Abacus. That picks up where SolidWorks Premium leaves off. Really good for multi-physics, high-speed dynamic events, lots of contacts. So you can see these are some results from Simulia Abacus. The collapsing of that structure on the right, or the cold rolling of materials on the left. You can also have your high contacts, like the collapsing of the Jenga blocks, crash tests. Those all look really cool. Damage modeling as well. So specific events, how much damage is going to occur, how much life can be in your product afterwards. Simulia can basically do it all. Now, if that looks really cool, but kind of too hard or complex, don't fret, because we offer simulation consulting services as well. So if you're like, oh, that looks really good, but it's only for a one-off product, I don't really want to buy the software for that. Well, don't worry, we can join your team for a bit and help you with whatever engineering challenges you have. So we have over 90 engineers from a wide variety of backgrounds. And then we got two kind of different packages you can choose from. You can choose the simulation flight plan, where you buy the software and then we will mentor you in a specific area. Or we have our analysis consulting, where you just give us your specs and we'll kind of do it for you. It's really good if you're in a crunch or you don't want to buy the software for yourself. A couple examples of some of the consulting we've done, but tons of information on our website, or of course you can always reach out to your sales rep. I'm sure they would love to chat to you about it. But now I'm going to kind of peek into that question panel to see if you guys have any questions, but that is all I have to formally show you guys. I'm going to turn my camera back on now. You can see my, there we go. You can see my face. Thanks for listening, guys. Much appreciated. I hope you liked it and learned something good. But it looks like Silvio was on it.
Yeah, great job, Dane. The only thing I would say, I was able to answer all the questions directly there, so hopefully you guys saw that. I would say that the features that Dane showed are part of the simulation add-in. So if you're not using that, or if you're just using Simulation Express, those functionalities don't exist there. So Sim Express, of course, is a limited functionality, but still doing linear static analysis. But if you want the full-blown functionality you saw today, that's a simulation add-in that we can discuss on a later time if you would like to see what that's about.
Cool. Right on. Thanks, Silvio. Yeah, I'm just going through the chat. Yeah, you nailed them all.
Yeah, so a question just came up. Basic simulation comes with any SolidWorks package, I guess. So any CAD level, so standard, professional, or premium CAD does come with Simulation Express, which is a kind of a dumbed down version of doing a linear static analysis. But if you wanted to do more functionality, like mesh controls and the hotspot diagnostics, like what you saw from Dane's presentation, that does require a simulation add-in starting with Sim Standard. So there are different levels to simulation as well that give you that functionality. Or if there's other modes of failure that you want to test for, like vibration or nonlinear and all that, that requires another simulation add-in as well. Yep, there you go. There's the matrix there. So Lucas just had a question, how do I change the first order? How do I change from first order to second order elements? So all that means is how do I change from draft quality to high quality? By default, it should be high quality mesh. When you're in the mesh interface, when you create a new mesh, there should be an option there to switch it to draft. Oh, I think you're muted there, Dane.
Yeah, you saw my hand gestures though. Yeah, depending on what year you're on as well, because they did move it in 2019, or in 2020 they moved it. So in 2019, it's in the Mesher tool under the advanced options. There's a little checkbox for draft quality. But in 2020, there's a whole separate tab on the Mesher where you can choose which body or which part you want to be draft and which ones you want to be high quality as well. So it kind of depends on which version you're using. SolidWorks Premium does include simulation, yes, for FEA.
Saul just had a question. Can you speak a little more about your analysis consulting services? So I can take that one, Dane. Ultimately, what we offer is, we're able to help you out if you don't have the tools. So if you don't have the license or if you're in a time crunch, we'll be able to take your problem and set it up within our tools. So within that, it requires us to, discuss with you what you're trying to get at, what type of analysis you're trying to run, what you're trying to get out of the analysis to see that it is feasible. But it is an hourly rate consulting project where we offer you a statement of work. We do the work for you, and we provide a formal report as well. So I can upload here some information in terms of the consulting services from our website. So just give me one sec here. So I'm going to post that in the overall chat here with the link. There's a couple of data sheets there that you can download within that web page that provide that information, but similar to what Dane had there on the slide there.
So the question of which level of analysis is in SolidWorks Premium. So you can run static simulations on parts or assemblies. So just this little kind of brick in the top left, static for assemblies, is what is included with SolidWorks Premium. Hey, glad you guys like the template. I thought it was pretty cool. I'm not as good in Excel as I used to be, but I tried to make it as automated as possible.
Hey, Dane, a question just came up in the chat with, can you go over a little bit more on the differences between P and H adaptive mesh? Are you able to?
Yeah, totally. So I don't have the ideal slide for that, but let me go back to one I think might be helpful. So the P adaptive and the H adaptive are kind of two different methods. So the H adaptive is, H stands for the characteristic element size. So that's changing the density of the mesh. The P adaptive is polynomial order. So what we have normally with our mesh elements is we have our draft quality, which is linear between the nodes. We have our second order, which is second order polynomial between the nodes. The P adaptive method doesn't change the size of your elements. It changes the number of nodes within the element. So then you will have two midpoints between the node, and you can have a third order polynomial, and you can go all the way up to fifth order polynomials for that P adaptive. So it's not changing your element size, it's changing your element quality. Did that kind of answer that question there? I think.
That's pretty much it then.
All right. Lucas, do you want a better explanation of where that button is to change to draft quality versus high quality? I can pull the software up and give you a nice little peek there. If you're still here, but if you moved on, it's all good. When would you use P versus H? Honestly, I kind of use them both. So what I'll do is I'll do an H adaptive to get my mesh looking dense in areas. And then if I'm finding, okay, my degrees of freedom are getting too long, then I'll just change the quality as well. So I'll start off with the H adaptive because it's way easier for me to visualize and I can see what's going on more. And because the P adaptive has a ceiling. So I can only go up to 5 fifth order polynomial, whereas with the H, I can just keep making my elements smaller. So I'll do the H adaptive first and get it looking really good. And then if I still haven't refined it enough, then I will copy the mesh from my H adaptive study into a new study and then do a P adaptive mesh and take that really good refined mesh and change the order up. But I just personal preference, I like to use H because I can see it better. Whereas the P adaptive, it's you got to do a bit of post processing to see the element quality. So when you say the weld tool, sorry, Dorian, this is your question. So the weld tool does create simulation usable geometry. You just need to be a little more specific on what you mean by weld tool. So if you're using weld mints, then those weldment structures are automatically created to beam elements. There is a weld connector inside of SolidWorks simulation, which will allow you to simulate like radial welds. But if you're using like a weld, like a graphical weld inside of your drawing or inside of your weldment's feature, then if it's not actually solid geometry, it's not going to translate into the simulation environment. No, the weld itself lines on the drawing. So if it's not modeled in the CAD geometry, it's not going to have solid elements attributed to it inside of simulation. However, inside of simulation, you can use a connector to simulate different welds.
Hey, let me answer a couple of questions here. So again, about the recording. So when you log into the main event page, there under the session where you initially logged in, there should be a replay option there. So once you log into that main page, you should see under Dane's presentation that you can view the recording after the session has ended. Any tips for going between beam elements, solids, and sheet metal when it comes to meshes? So again, if you are designing using weldments or designing using sheet metal surfaces or just using normal SolidWorks features, when you throw that into simulation, it'll automatically account for, it'll automatically convert it to the appropriate mesh type. If you have all solid components and you want to convert it to a shell, you can right click on that body in the sim tree and say, use selected faces to convert to a shell or convert to a beam. So it's just a simple right click on those bodies to convert it from one mesh type to the other. Or again, if you designed it in those formats, it'll do it automatically. All right. Well, I think Dane, I'm not sure if there's a 12 o'clock session, but we want to make sure we give him time to log into that one. But definitely let us know if you have any questions there.
Yeah, so yeah, that is everything that I wanted to show you guys. I'll be around in some of those round table things in the next couple of days, so you can always find me in there. I'll be in the CAD one. Yes, you can totally mix meshes. And since they have different degrees of freedom, the meshes, you have to sometimes add connections as well. So that training class that we linked to has a bunch of lessons on the mixed meshing. Unfortunately, in like the 3 minutes I have left of this chat time, I can't really get into that. But yes, you can do mixed meshing, and there's a bunch of techniques to utilize that. The recording will stay inside of this kind of conference. So you can log in tonight, tomorrow, the day after. I'm not sure how long it will be up, but these will all get put onto YouTube afterwards as well, or at least so I'm told.
Yep. I believe that is the plan, yeah.
So you guys can make me a YouTube star.
No problem, everyone. Glad you guys joined.
Yeah, have a great rest of your day, and feel free to come find us in the roundtables.